Hi everyone. So today we'll be doing exercise 1.2 from NCERT Mathematics Class 9 from the chapter Number Systems. So the first question out here is a simple true or false question. It has three parts. We'll talk through it and we'll try and justify our answers whether they're true or false. So the first statement says every irrational number is a real number. So this statement is absolutely true, since the definition of real numbers is the collection of all rational as well as irrational numbers. Everything that can be represented on the real number line consists of a real number, and irrational numbers are no exception to this. So the first one is definitely true. The second statement says every point on the number line is of the form root m, where m is a natural number. So we know that any point on the number line would be a real number. This real number could be a rational or an irrational number. But if it's in the form root m and we are constricting m to be a natural number, then this is not true for every point on the number line. And how do we know this? Let's take the help of an example over here. The number pi. We know pi is a non-terminating sequence from our earlier classes. It's roughly 3.14 is what we take when we do our calculations. However, there are multiple numbers beyond the third and fourth and fifth decimal point, and this is a non-terminating sequence. How do we know that it cannot be represented in the form root m? So let's say we could represent pi in the form of root m, right? This would mean that if we square both sides of the equation, we get pi square is equal to m. And if you remember, the second part of the statement says that m is a natural number. Now the square of pi is definitely not a natural number. It will be in its decimal form or its fractional form. However, it will not be a positive natural number. It will also be a non-terminating sequence, which would imply that pi square is also irrational and hence cannot be a natural number. So because this statement of ours is validated, our initial assumption of pi being able to represent in the form of under root m is not true. Hence, we will say that this statement is false. Moving to the third statement, says every real number is an irrational number. This is the exact opposite of our first statement. We know that every irrational number is a real number, but the converse may not be true. So as per the definition of real numbers, right? I'm denoting real number by the capital letter R. It consists of two things. It consists of all irrational numbers and it consists of all rational numbers, right? So every irrational number will be a real number, but a real number will not necessarily be a rational number. An irrational number, beg your pardon. An example of that is a rational number, say the number 2. 2 is not an irrational number. It can be represented in the form p by q, which is where q is not equal to 0. And by this I mean in the form 2 by 1. Hence this statement is also false. We'll move to question 2 of exercise 1.2. Question 2 says, are the square roots of all positive integers irrational? If not, give an example of a square root of a number that is a rational number. So the answer to this question is, as you would have guessed, no. Square roots of all positive integers are not irrational. We do know root 2 is an irrational number. We know root 3 is an irrational number. However, root 4 when simplified equals 2, which is a rational number. How do we know it's a rational number? You guessed it, the same equation. It can be represented in the form of p by q, where q is not equal to 0. How do I represent 2 like that? 2 by 1. So this proves that the square root of every positive integer is not an irrational number. The next question of exercise 1.2 is, show how root 5 can be represented on the number line. And I've taken a physical paper to demonstrate over here because this requires a bit of construction. So if we see the number root 5, if we have a rectangle of sides 2 units and 1 unit, do you know what will be the length of the diagonal of this rectangle? It's a simple Pythagoras theorem. 2 square plus 1 square, which is 4 plus 1 under root, which is root 5. So essentially, if we construct a rectangle of length 2 units and 1 unit, the diagonal will be of length root 5 units. And then we can extrapolate this on the number line. So now let's get to the construction and see how we will figure this out. Let's first draw the number line. Let's label a point 0. And let's make the rectangle with the side of length 2 units on the number line and 1 unit as the perpendicular. Now to draw a 90-degree angle over here, I'm going to use the compass. In case you don't know how to draw a 90-degree using a compass, that's fine. We learned that in chapter 11 in the constructions chapter. In the meantime, you can maybe use a protractor or a set square to measure a 90-degree angle and draw the 1 unit side over there. I measure 1 unit on this 90-degree line. And let me name this point as A. Now if I join OA over here, this line is for root 5. And how do I represent it on the number line? I open my compass with center O and length OA, and I simply extrapolate this length on the number line out here. Let me call the intersection of this construction on the number line as B. OB for me is the required length on the number line of root 5. If I am to measure OB with a scale, it comes out to be somewhere between 2.2 and 2.3. We know the value of root 5 to be 2.236 till its third decimal place, and then it's a non-terminating sequence. So this validates our construction of OB being root 5, and that's how you represent it on the number line.